All right, welcome to Lecture 1, Part 1, for the Real-Time DSP course here at the University of Texas at Austin. Any questions from the last two lectures? Okay, so I've assigned the first homework assignment. I sent that by email this morning. So this lecture will be generating sinusoidal signals. You'll need this for homework 0 and also lab 2, which will be next week. And the outline here will cover half today and half on Wednesday, so Monday's a holiday for Dr. Martin Luther King. Okay, so outline, we'll cover bandwidth today and get a little bit into sinusoidal amplitude modulation, and we'll cover the last two bullets on Wednesday on design trade-offs and some preview of lab 2. So first let's talk about bandwidth before we get into the details of generating sinusoids. So some of this is review. But it's good to have a similar or the same definition of bandwidth as we... Could someone close the back door? But if it's locked, is it locked on the back door? Then try to prop it open if you can. So for bandwidth, we define this as the non-zero extent in positive frequencies. And it kind of implies that negative frequencies are mirror images or somehow obtained from the positive frequency extent, and we can do that, and we will do that. So for our case, again, bandwidth is non-zero extent in positive frequencies, and the problem is, how do you really define what extent means? So in the ideal case, it's easy. So here's the ideal case. For a low-pass spectrum, we assume all the content is between minus F max and F max in hertz, and there's no content, or zero content to be more precise, at frequencies other than between minus F max and F max. So the bandwidth here is F max. So we assume that the bandwidth here is 0, and the bandwidth here is 0. So bandwidth, the frequency content at frequencies above F max are 0, and the frequency content at frequencies below F max are 0. For the bandpass case, the ideal bandpass case, it's very similar. We also assume idealism here. So we assume that between the spectral clustering that I have shown here, the frequency content is identically 0. So we have content from F1 to F2 and a mirror image between minus F1 and minus F2. Okay. So in this ideal case, it's pretty easy to find the bandwidth. It's just the difference between F2 and F1. It's the bandwidth in hertz. We can apply this to both continuous time and discrete time signals. That is to say, to continuous time frequency in hertz, or equivalently radians per second. We can also do it and apply the definition to discrete time signals. And what's the frequency in discrete time? What are the units for that? I hear bits per second. Do we have any seconds left in discrete time? Did they go away? Yeah, they're gone. So in discrete time, we talk about samples. So the frequency content is a different unit, and we can say radians per sample instead of radians per second. We'll talk more about that as we go, and we'll talk more about that on Wednesday as well. Okay, so we have frequency, the knowledge, some concept of frequency in both domains. Now, in practice, the spectrum will not, go ahead. It's F max. So again, it's the non-zero extent in positive frequencies, so we just look at what happens in positive frequencies, and the extent is from 0 to F max. That width is F max.
So whereas in the bandpass, it's okay.
Right, so it's F2 minus F1 in the bandpass case. Right, so this is our bandwidth here. So we focus on the positive, right on the... So it's this. That's pretty scribbly, isn't it? Okay, so it's this part of it, right? It's a positive part. Yeah, go ahead.
So we measure discrete time in radians per sample.
Yes.
We still measure in hertz as well.
No, but we can work back. We can interpret a discrete time frequency as a continuous time frequency if we know the sampling rate.
Yeah.
Okay, so there's a connection, but as a unit, this would be radians per second. So in practice, the spectrum won't be ideally band limited. There are more than two reasons, but I'll give you two reasons why this isn't going to happen in practice. This is wonderful theory. It's a good starting point, but it's not the ending point. So there's at least two other issues to think about. One is thermal noise has a flat power spectrum that goes to pretty high frequency, out to 10 to the 15th hertz. So I have two questions here for you. One is, what is thermal noise? You can go for it. It's from?
Just from, I mean, like in a circuit, you have thermal noise generated from the heat electrons passing through.
That's correct. So it has to do, well, yeah, so there's ambient temperature in which a system is operating, could be a circuit, and that temperature creates noise. Higher the temperature, higher the noise, more noise. Where does it come from for us as in electronics? So where does that thermal noise show up? It could be radiation, but in a circuit, what's happening?
Power dissipated.
Could be power dissipation, but how's that? What's the physical mechanism? What's moving around?
Current.
Electrons. So it's a random motion of electrons due to temperature. This is always there, wherever we are in our system, circuit. And this thermal noise has a flat spectrum from 0 to 10 to the 15th hertz. Now, this is a high frequency, and this class is in discrete time, primarily in discrete time processing. Of course, we make connections to continuous time quite often. But to get to discrete time, I have to sample some signal at a rate, and this is much higher than any sampling rate I would use in practice. And so our sampling rates now, tens of gigahertz is kind of where we're at in off-the-shelf test and measurement equipment. It's hard, So that's 10 to the 10, maybe 10 to the 11 if you really got some really good stuff. 10 to the 15th is way beyond what we would sample. So for the frequencies we care about, we're going to have thermal noise. And I forgot what happens beyond 10 to the 15th. I remember having this in class as an undergraduate student. I don't remember what happens beyond. I remember it falls off, but I don't remember how.
Why would having that higher sampling rate make you care less about thermal noise?
Well, no, we do care about thermal noise because the frequencies we care about in a discrete time system go up to tens of gigahertz. So the kind of right now where we end up, you could argue either way, but 64 gigahertz is kind of our upper limit where we care about right now. So we do communications where we do sampling and discrete time work up through about 64 gigahertz because there's an open ISM band between 57 gigahertz and 64 gigahertz. There's some optical communications that goes higher rates than that. But for us doing electronic sampling, we're down below 64 gigahertz. So the whole spectrum we care about, we've got flat. We've got basically thermal noise equally present at all frequencies. Okay, so if I were to sketch this power, and I have to do a power spectrum for this one, which is a magnitude squared, which we'll talk about on the next slide. This thermal noise, basically as a function of frequency, this would be the power spectrum, which is equivalently the magnitude squared, if you will. So this would look like this. So basically, I've got noise present at all frequencies, equally present at all frequencies. Again, it's an idealism. The real story is that there'll be some, a little bit of wiggle here and there in practice. The theory says it's a flat power spectrum. Now, the other way that we can get that the spectrum won't be ideally band limited is in practice we can't observe a signal for all time. We have to look at it over some snapshot of time, and because of that finite observation, we are going to have infinite bandwidth. We'll see this on homework 0 in particular. Okay. So for two practical reasons, our spectrum will not be ideally band limited. We're not going to see this in practice. It would be nice, right? So if we're not going to see this in practice, these ideal spectra in practice, we have to come up with some other way to measure this. Okay. So let's talk about some alternatives to this ideal non-zero extent. So let's take the low-pass case first. Low-pass case, we would like to approximate a a spectrum or a frequency content we might see in practice using the ideal model, right, which is this ideal of band-limited spectrum. So let's look at what we might have in practice. So in practice, we might have something that has significant content, frequency content, at low frequencies. And then what you see out here is, what do you think these tails are? Noise. This is where your thermal noise is. Okay? So eventually, if we have a low-pass spectrum, we're going to eventually get to high enough frequency where the noise is stronger than the signal. The noise swamps the signal. Frequency content. Go ahead.
So does the noise and the signal add up?
Yeah, for the case of thermal noise, the answer is yes. The question is, does noise and signal add up? For thermal noise, yes. It's just additive noise. It's independent of the signal that we're generating or transmitting. It's just there. It's just from the random motion of electrons. So it is additive in this particular case. Sometimes noise is not additive. And we'll talk about that a little bit later. But for our cases, and for most of the class, the noise will be additive. So here's a signal that we care about that's low frequency and noise that's, really the noise is at all frequencies. Sorry about that. A little sensitive. I said no. Too sensitive. There it is. There we go. A little too sensitive there. All right. So the noise here is really more or less flat over all frequencies. But where the signal has more power than the noise, you're going to see it as really just squiggles here along the spectrum. It's additive. So I have some signal spectrum, and I'm adding to that this noise spectrum, or the noise, actually signal plus noise. That's what I'm really looking at. And I'll see the noise where the signal power is weak. And I'll see mostly signal where the noise power is weak relative to signal power. So now I'd like to approximate this. Again, I've sketched this by hand, but a closer to reality spectrum. I'd like to approximate this as an ideal spectrum, just to talk about bandwidth. And I'll need to know bandwidth for lots of reasons. As soon as I start plotting the signal in MATLAB, I have to sample it. I have to make sure I sample it more than what? If I know F max, how fast do I need to sample the signal?
Twice.
More than twice F max. So that's the sampling theorem, which we'll talk in much more detail later. So if to sample, I'd like to sample at some rate greater than 2 F max. But I have to know what F max is, or at least an estimate of F max. Strictly speaking, if I apply the ideal spectrum definition, this noisy signal never had, the F max isn't really as high as I want it to go, infinity, really, in theory, 10 to the 15th perhaps in practice. So I can approximate this noisy spectrum using the ideal model a couple ways. One is really useful in lab, and even useful when looking at plots of spectra. It's just a quick way to get an estimate of F max. And later, when you have time, you can come back and do something more quantitative and mathematical to verify your estimate. Fastest thing, quickest way to do this, apply a threshold and eyeball it. So you can say any spectral, the amplitude here in my spectrum, if it's less than a certain value, we're just going to call it 0. We're going to say it's negligible, and we're just going to truncate it. So you have to figure out what that is. So you have to figure out, okay, I have to pick a value, and I really want to pick that value above the noise floor. This noise is roughly constant over all frequencies, the noise power. Sorry, noise spectrum. All right, so let's pick, let's see how this shows up. So I can pick, say, this point. Anything below that we'll call 0. So it's arbitrary, ad hoc, quick way to estimate this noisy spectrum as an ideal spectrum. And once I've done that, now I can start I can eyeball F max. So where's F max? It'll be right there. That's my estimate of F max. How visible is the color in the back row? Not so much, all right. So that's our approximate here. Our approximation for F max is right here at this corner, where it matches the threshold. All right, that's the quick way to do it, and this gets us most of the answer, most of the way to an answer. And again, in lab or homework, it's a good way to go because it's quick. Now, if you want to go back and make sure that your estimate is accurate with some measure of a more quantitative measure, then we can start talking about what's called the power bandwidth, which is in the book. It's in Johnson, Tharson, Klein. So the power bandwidth approach says we're going to estimate F max so that I capture a certain percentage of the total energy in the frequency domain. What does that mean? It means I have to find the smallest value. That's why I have the minimum here of F max. The smallest value of F max, that when I integrate the magnitude spectrum squared, this is the power spectrum. So if you think about what's power, it's something squared. What is capital H of F? It's the frequency content at a particular frequency F. And it's going to be complex valued, generally. The absolute value squared gives me magnitude squared. This is a power calculation. So this gives me the power at a specific frequency F. All right, so this is power. This term is power at frequency F. If I integrate all that power over frequency, I get the energy. So I can say, well, what's the smallest value of F max that gives me 90% of the total energy? How do I get the total energy? Well, in theory, I integrate the power spectrum, again, magnitude squared, over all frequencies. Because bandwidth is the extent of positive frequencies, I'm only concerned with really positive values of frequency.
Wait, so is the quantity h of f squared that magnitude power, or is it?
It's the magnitude squared is the power. So this whole thing is the power spectrum. So it's the power at a frequency F.
Isn't this just sort of another way of applying an arbitrary threshold?
It is another way of determining a threshold. It's less arbitrary than eyeballing it. But it is arbitrary because it is arbitrary. Why do you say it's arbitrary? Because it is. Where do you see it?
You just pick the number
0.9, exactly. So where it is arbitrary is the selection of where do you draw the line. And here I'm doing 90% of energy. You could do 99% of energy. You could do 95. That's where it's arbitrary. It's your choice. Go ahead.
Can you explain again the minimum frequency max?
Mm-hmm.
What's it do?
So this is saying find the minimum F max for which, when I integrate the power spectrum, I get 90% of the energy. So what I'm really looking for is the F max value that would give me the equality if I could. So let's say, let's say, a kilohertz gives me 90%. So 2 kilohertz might give me 92%. But the answer I really want here is the smallest F max that gives me 90% of the energy. Okay. Now, this does look arbitrary. What will happen is if we pick F max according to this formula and we sample at just above 2 F max according to the sampling theorem, it tells us how much energy aliases. Okay, so even though this 0.9 is arbitrary, which it is, it tells us that if I pick the sampling rate at just above 2 times F max, 10% of the energy will alias. Okay. So if I want to control the amount of aliasing, I can make this 0.99, and now suddenly I only have 1% of energy aliases. So it just depends. So that's where It's your choice. How much aliasing do you want to put up with in your system? Now, there's a little bit of more effort here to make this practical because I have infinity. That's hard to measure. And I'd also like to do this with a measured spectrum in the lab. So there's ways I can do that. So lab equipment, spectrum analyzers, will let you download samples of the spectrum taken every so many hertz, say every 10 hertz or whatever you set it to. And you can download those samples into a laptop or so forth, a PC, whatever. And you can integrate by just simply adding up all those magnitude squared values over as much frequency as you want to work with. And the spectrum analyzers in the lab won't measure out to infinity. They'll measure out to some maximum value. And so what you can do is use that large maximum value in place of infinity. So infinity here is something much greater than the frequencies that you care about. So if you care about something in the, let's say, kilohertz range, then you might measure all the way out to a gigahertz. That's your infinity. That's just so much greater than where you're measuring. So in practice, so again, it's still an estimate. So we, again, can use lab equipment, download those values to get an estimate. But it's amazing how good the first method, as ad hoc as it looks, it's amazing how accurate it is if you have a good threshold. And you eyeball it well, you'll get a pretty good value. You might get 90% of the right answer. It's good enough. Because the way you're going to use it is to pick a sampling rate. So here, the sampling theorem says, okay, the sampling rate should be more than 2f max. You can make the sampling rate more than 100f max. So you can be very kind of sloppy in the estimate of f max as long as you sample at a lot more than 2f max. Sample at, say, 100f max or 10f max. You can have a little bit of error in f max. It's okay. Any more questions on this one? Okay. Now I could also, instead of having magnitude squared, I could just have had magnitude. I pick, so I don't have to have a square here. It's up to you. This is a convenient measure because it relates power and energy. Talking about power bandwidth and how much energy aliases. Okay, and as a review from last time, this example here of a low-pass spectrum, this is, again, a baseband signal. The energy in the frequency domain is concentrated around DC, and DC means zero frequency. Average value in the time domain. Okay, so let's do this for a bandpass signal. Similar approach. So here I have a bandpass spectrum and noise, so I have spectral content centered around FC. Now, FC could be a carrier frequency from a communication signal. Have to be. This is the center of the band we care about. So you think of C as center, if you like, so F sub C. So we kind of, in advance, we kind of know what FC should be, some approximate value that it should be based on the standard we're working with. And then the question is how to find F1 and F2, basically how to find the real bandwidth here, or an estimate, really, of the bandwidth. And again, if we threshold this, so again, we can see the noise show up. The noise floor is showing up here and here. So it's noise adding on top of our signal. So then you can also see the noise where the signal power is stronger than the noise power. So if I use the red point as my threshold, and then interpret any in this case, magnitude here, the magnitude of the Fourier, magnitude in the Fourier domain, anything less than this threshold, again, we're just going to approximate as 0. And this gives us an ideal bandpass spectrum. So if I have to eyeball what F1 is, I suppose it's right about there, and F2 is probably right about there. And I'll draw a hat to say it's an estimate. Okay, and so now we have an ideal spectrum. We've interpreted this noisy spectrum as ideal just from thresholding. Again, works pretty well in practice. Because in the end, these F1, this F1 and F2 are estimates. They can have some error in them. It's okay. Now we come back and do the same kind of thing in the previous slide, which is to have a quantitative way of estimating F1 and F2. Now the good news is it looks like we have two parameters that we have to find. The good news is we really just have one, if we assume knowledge of the center frequency FC. Okay, so some examples. If this were AM radio broadcast, you want to tune into the zone 1300 kilohertz, you know what FC should be. If you're working with Wi-Fi, you're in the 2.4, at least in the 2.4 gigahertz band of Wi-Fi, you know where the center frequency would be. It's based on the standard. It's somewhere between 2.4 and 2.499 gigahertz. Based on which subchannel you pick up in there, which 20 megahertz subchannel, you know where the center should be. You also know if you're looking at the whole ISM band at 2.4 gigahertz, the center frequency is going to be at 2.45 gigahertz. So you kind of know what you're looking for in advance. Go ahead.
When we had bandpass signals like this,
Mhm.
if we were to want to sample it, we would just take the upper. Would we just take the upper end, like F2? And say
Correct.
we
So the-
sample at least at 2 times F2.
That's correct. So the standard sampling theorem says, again, that the sampling rate has to be greater than 2F max. Now, in this case, F max is going to be F2. Right? Now, there's another version of the sampling theorem called bandpass sampling, which we will talk about really not until March 2nd, or March 3rd. It's coming. Okay, so there's a way that we can reduce that sampling rate dramatically. And I'll just tell you the punchline. The punchline is that the sampling rate just has to be greater than the bandwidth, F2 minus F1, which is much smaller than 2 times F2. Okay, there's some. We'll get to that later in lecture 4 slides. But for now, if we're going to plot this in MATLAB, we want to go with 2 times F max. Or anytime we apply the standard sampling theorem, we want 2 times F max. And again, greater than is it's strictly greater than according to the theorem. Now we'll talk about in lecture 4, there's some ways we can make that greater than or equal to. There's some risk in there, but the standard statement of the theorem is greater than 2F max. So in the end, we're looking for one free parameter. If we know the center frequency, now we just have to find an estimate of the bandwidth of this bandpass spectrum, and we're going to call that capital W. So capital W is this. It's this distance. There we go. Capital W. So now the problem becomes, I want to find the smallest bandwidth, capital W, for which I capture, again, some percentage of the energy. And again, here I'm using 0.9. That's arbitrary. And now the integration that I do is over my estimated transmission band. So I'm going to go from FC, which is the center of the band. So there's FC. Just have a super sensitive pen today. So FC, and that means that F1 is FC minus half of capital W, and F2 is FC plus capital W over 2. So the band of frequencies that I'm measuring is between FC plus half W, which is F2, and FC minus half W, which is F1. And the only free parameter in here is W, capital W, because I'm assuming knowledge of FC, the center frequency. And then the total energy is calculated as before. It's over the whole frequency band that I care about. Now, there's a limitation, though, now on capital W, which we didn't see before. Because if I make W too large, I eventually get to the point where I occupy from 0 to 2 times capital W. So that any solution of capital W that causes this right cluster of frequency content to be wider than 0, or actually the left edge goes negative, that doesn't make any sense. So we have to constrain the answer here to be between, of capital W, to between 0 and 2 times FC. If it's greater than 2 times FC, the left edge goes negative, which doesn't make any sense. So in practice, what I've found is that for this particular case, the thresholding actually works better than the formal quantitative method, because what I've found in practice is often this formal method gives me a left edge that is negative. So it doesn't really help me much. So we'll see this in homework 0. I would suggest in homework 0 to eyeball it. It's good enough.
Why does it give you a left edge?
Because what happens is there's so much frequency content left and right of this. It picks up all that as in the energy, and I just have so much more spectrum out here that it throws off the value of capital W. So one way around that is to reduce the 0.9 to say 0.7. All right, this is arbitrary. This 0.9 is arbitrary, so you could change that to get a more reasonable answer for capital W. It's like anything. If you get an answer back from a calculation, you want to sanity check it to make sure that it makes sense as an answer. Okay. Any questions on this? Any more questions on this? All right, so let's talk now about, now we've got a good or better handle on bandwidth and a formal definition to work with, which is extent and positive frequencies. Let's now talk more detail about up conversion, which we talked on lecture 0 slides. One way to perform up conversion is to multiply by a cosine of fixed frequency. This cosine of fixed frequency has a fixed frequency of omega c, which is in radians per second. And this is 2 pi times fc. I think the finger is going to work better than the pen, so we're going to go with the finger. All right. So 2 pi fc. So fc is in hertz. Not so much. fc is in hertz, and omega c is in radians per second. Mathematically, this is simple. The implementation is a little more involved. But multiplied by cosine of fixed frequency, omega c, I now, if x1 is baseband, then what will happen is, as we saw in lecture 0, the bandpass spectrum, x1 of capital omega here, shifts to the right by the carrier frequency and to the left by the carrier frequency, and I scale by a half. We're going to use this all the way until the last week of lecture. This is just a fundamental thing that we'll do. So again, if we assume x1 of t is an ideal low-pass signal with bandwidth omega 1, and that omega 1 is less than omega c, you don't need the much less than will do it, then I get this up conversion relationship between x1 and y1. So now, as I asked in lecture 0, y1 of omega has a transmission bandwidth. So the bandwidth of x1 is w1. The bandwidth of y1 is 2 times omega 1. Right, so this whole baseband spectrum is shifted right and left. So the bandwidth ends up doubling as a result of this up conversion process. if the spectrum x1 of omega is real valued, the spectrum of y1 of omega is real valued. We'll use this to our advantage in about 2 slides. So that's fine. That's up conversion. Now, we'd like to do, which this is sinusoidal modulation to perform up conversion. We'd like to be able to, of course, go the other way. If we have a bandpass, this is for transmission. We want to transmit the bandpass waveform, the bandpass spectrum. On the receiver side, we're going to receive the bandpass spectrum, plus noise and other things we don't want to keep around. So what we'd like to do on the receiver side is to take the bandpass spectrum and go the other way, go back to baseband. And we can do that by applying, in the case of sinusoidal modulation, sinusoidal amplitude modulation, is to multiply by a cosine and then low-pass filter to pick off the baseband spectrum. Let me try to draw that for you. All right. So if I start with the bandpass waveform, y1 of t, and I multiply by a cosine of the same frequency, omega c, what will happen? This bandpass spectrum will shift to the right by the carrier, omega c, and to the left. So this whole thing shifts right, so this left band then ends up centered at the origin. The right band moves out to be centered at where? 2 times omega c. The right band shifts left. Sorry, right. So this band shifts 2 directions. It shifts right by omega c and left by omega c. So it shifts to the origin in minus 2 omega c. This right band shifts to the right by omega c and to the left by omega c. So it ends up centered at 0. So the spectrum that I get as a result of this second modulation is I get 2 clusters at 0. I get 1 cluster at 2 omega c. And I get another cluster at minus 2 omega c. Now, this is nice because now I can get my baseband signal back by low-pass filtering and extracting it. This low-pass filter will pass low frequencies that I want and attenuate and reject the high frequencies that I don't want. So the dual process is, again, just applying the sinusoidal modulation followed by low-pass filtering. So again, this is the spectrum this is the Fourier transform of y1 of t times cosine omega c of t. So the rest of the story then is I need to apply a low-pass filter, and what I get out is an estimate of x1, which I will call x1 of t with a hat. See if I can do this with a... All right, so that's an estimate of the baseband signal. Go ahead.
So when you get the y1, what you're doing is first you're multiplying it by a cosine, and then you're multiplying it again by the same thing.
Yes. So yes.
So it shifts it, and then it shifts that again.
Correct. Okay. Right. So this is on the receiver side, and this is on the transmit side. So y1 is the output of the transmitter. Then the receiver receives that, and in practice plus noise, but for now, it's all ideal. The transmitter transmits Y1 of t. The receiver receives it. The job of the receiver is to try to get back to baseband, which is the original signal. Again, audio, speech, if it's AM radio, for example. That's what we want to listen to. So the Y1 of t then goes through this multiplied by cosine, low-pass filter, and we now have an estimate of x1 of t. If there's no noise in the system, no other distortion between transmitter and receiver, I get exactly back x1 of t if I do ideal operations. In practice, this will be a noisy estimate. And there will also be a delay because I get delay. Any sort of filtering I do will have some delay. So in practice, this is a delayed and noisy version of the original bandpass waveform at the transmitter. Okay.
Just to check, so after the low pass filtering, the bandwidth is going to be omega 1, right?
Yes, that's right. That's right. So the low-pass filter is going to pass frequencies from 0 to omega 1. All those frequencies come through the filter, no problem. Frequencies above omega 1 experience some reduction in amplitude. And eventually, the reduction is so great that it causes these two bands to be essentially suppressed to the point where you wouldn't hear them. That's the hope. So there's a filter design issue here, which we'll talk a lot more as the class goes on. So I remember a couple semesters ago, a student asked if we were going to do filtering in here, and I had to think about it. I think 50% of what we do is filtering in one form or another. So we'll do a lot of filtering in the class. So we'll talk a lot about how to do this particular low-pass filter, how to design it, how to implement it as we go. Go ahead.
What's the definition of the lower side pass?
Yeah, so this is just an operating definition. What's interesting here is that we've doubled the bandwidth that we need. It's wasteful. So just to point out that if I know the lower side bands, it's enough information to generate the upper side bands. So I really have twice as much information as I really need in my transmitted signal. And we'll talk about how to recover this inefficiency in a couple of slides. So it's just a definition. All right, let's talk about amplitude modulation by the sine. It has a very similar idea. Very similar story in terms of how bandwidths are used inefficiently. So here I want to do on the transmitter side, I want to take a baseband signal x2 of t multiplied by a sine at fixed frequency omega c. A similar thing happens. The baseband signal x2 of t, and here I show the spectrum capital X2 of omega, shifts to the right by the carrier frequency, shifts to the left by the carrier frequency, but instead of being scaled by a half, it's now scaled by a half, which is the same, but now I either have a j or a minus j. And this has to do with the Fourier transform of the sine. It has these different factors in them versus the Fourier transform of the cosine. But the bandwidth use is the same. The transmission bandwidth is what? The transmission bandwidth is still twice the bandwidth of the baseband signal. So 2 times omega 2 in this case. If x2 of omega is real valued, then y2 of omega becomes imaginary valued, and I'm showing the imaginary values here by these dotted lines. It's just a way to represent it. Now that's interesting. So if I do the up conversion using amplitude sinusoidal modulation with a sine, SINE function, my baseband spectrum becomes, which was real valued, now becomes imaginary. In the previous slide, amplitude or sinusoidal amplitude modulation by the cosine gave us an upconverted signal that was real valued. Okay, so we can use this in just a second to gain back the inefficiencies. So it turns out if we subtract the two, they don't interfere with each other. Or if we add the two, they don't interfere with each other. Demodulation is the same idea. Demodulation, I have to first modulate with the sine and then low pass filter. So the demodulation is exactly the same story. So y2 of t multiply by a sine. And I follow this by a low-pass filter to pick off the baseband. And I have an estimate of x2. Trying to get my hat in here for the estimate. Destroying everything in its path. Okay, so here's x2. Again, we get an estimate of x2 at the receiver's output. Now, there are a few things in here that you might pick up on. One is this all works nicely in an ideal setting. There's no noise. The receiver knows exactly the carrier frequency used by the transmitter. Not practical. So we will talk about how to overcome these assumptions as we go through the semester. We will have the right algorithms to estimate the carrier frequency and do the right thing. That's coming in the second half of the class.
When you apply the second sine wave
Mhm.
or sine coefficient,
Yeah.
the two red sidebands that would come back to the middle
Mhm.
in order to make the are they both going to be upright, or are they going to be kind of like one of them?
Yeah, the good news is that what happens is, the questions that we multiply by the sign here in the receiver, the good news is I multiply again by j1/2, which now gets me, 1/4 and a negative 1/4. So I go, the good news is after I do this
Yes.
sine wave, the sine modulation in the receiver, I go back to real valued spectra. So yes, it's a good thing. All right, so now let's go ahead and talk about how to use bandwidth efficiently, knowing that I've got these two ways to do up conversion, both using sinusoidal amplitude modulation. One uses the cosine, one uses the sine. So now I can send two different low pass or baseband signals x1 of t and x2 of t over the same transmission bandwidth if I do the following. So I take a baseband signal x1 of t, modulate by the cosine, fixed frequency omega c, take x2 of t, which is a different baseband signal, modulate by the sine, omega c of t. If I subtract the two, they don't interfere with each other. Right? The spectrum of the result of modulation by the cosine is real valued. The result of the spectrum as a result of the modulation by the sine is imaginary valued. I add real and imaginary, I get complex, but the real and imaginary components don't interfere with each other. They are orthogonal. They're in different dimensions. Think about the complex plane. I have a real axis, imaginary axis. These are now on two different axes. They are orthogonal in the sense that the two axes are orthogonal in the complex plane. This is called quadrature amplitude modulation. It is the most common modulation method used inside of consumer electronic communication systems. This is Wi-Fi, DSL cable, LTE cellular. All of these use QAM in transmission. Now, the expression of in the Fourier transform domain is a little more complicated. Now I have two channels to worry about. So the Fourier transform of my transmitted signal, S of t. Again, I'm doing the Fourier transform here in radians per second, omega. So I get the original baseband spectrum shifted left by omega c. The plus omega c means shift left. Minus omega c is the one that shifts right. For x2, I get a shift left, a shift right, and a scaling by j1/2. This I get a scaling of 1/2. Another difference is the sign. The sign here is different in the two terms. But the similar structure. The baseband signal is shifted left by the carrier and to the right by the carrier. Go ahead.
To do this, to demodulate it at the receiver, does the sine and cosine there have to be in phase with?
Yes.
with these
So
two?
this makes the work at the receiver more difficult because, yes, the receiver has to have a cosine signal that's exactly the same phase as this and a sine signal actually it has to have a negative of the sine signal, because of the minus sign, that has the same phase as this, except we're negating it. Okay, and so that puts a lot of work on the receiver to estimate what that carrier frequency should be and what the phase should be. Has a little more work to do.
Doesn't it know it already?
It knows what it is approximately, but there's always some error. So the clock at the transmitter is different from the clock at the receiver, and then the transmission medium can wiggle that around a little bit. There's some, distortion of that as the waveform propagates through the channel. So we know it to a certain amount of accuracy. We just have to then lock onto it and find it. So the good news is there isn't a huge window to look over. Maybe there's 1 or 2% error, 3% error. It's a very small amount of error. So that's good. It means we have a very small window to look over. So again, just what I've already said in words, the cosine modulated signal, which is the upper branch, is orthogonal to the sine modulated signal in the lower branch at the transmitter output, or at the point of S of t. Now this orthogonality can be, can be altered due to propagating through a channel, going through circuits. So there's some work I have to do at the receiver end to restore this orthogonality before I extract the baseband signals. If we use the idealism of ideal bandwidths, no noise, there isn't much we have to do, except because we assume in the ideal case that we know omega c at the receiver. But in practice, we have a lot of work to do at the receiver. Okay, any final questions here before we call it a day? Go ahead.
When you talk about how you're going to demodulate it after
Yep.
the quadrature amplitude modulation, when you have done that, I don't know.
Yeah, I'll be glad to. I'll get a new slide here.
When you just do the reverse operation, basically.
Yeah, so the way you would do it is do the dual operation. So you receive S of t. So this is the receiver. Here's S of t. It's going to go through two paths. The upper path, modulate by cosine omega ct. Lower path, modulate by minus sine omega ct. Low pass filter. Low pass filter. I get an estimate of x1, estimate of x2. Okay. All right. So that's your demodulation block diagram in the receiver. Again, assuming exact knowledge of the carrier frequency and phase. That's how we would do it. All right, have a great weekend. See you on Wednesday.
We have no last section today, right?
Correct. Oh yeah, I'm sorry. Before you go, let me give you a quick introduction to Chow and Zane. I forgot to do that quickly.
Hi, I'm the TA of this class, and I will be in the Wednesday and Friday lab session, and my office hour from 3:30 to 5:30 on Thursday, and also from 5:30 to 10:30 on Friday.
Oh, hi, I'm Zena, associate graduate student. I will be the TA for Monday and Tuesday sessions, and my office hours will be on Wednesday from 3 to 4:30 and